Hello everyone, welcome back to my review video on AP Physics 1, this is Unit 3 on energy. So let's begin with working energy. So energy is the ability to change in state of motion or movement. Work is defined as the process of transferring energy by an external force along with displacement, which is the amount of energy transferred in or out for a system. In one dimension, and with a constant force, work is defined as the magnitude of force vector times the magnitude of the displacement vector times cosine of the angle between the two vectors. Note that the f and delta x must be positive after this magnitude operator. So this can be rewritten as the amount force parallel, the magnitude of force parallel to the displacement times the magnitude of displacement, and which is equal to the magnitude of force times the amount of displacement that's parallel to the force. This is from the definition of dot product, vector dot product. Let's say you have work is defined as F dot delta X. This is not tested. This is part of the AP Physics C curriculum, but this is not tested on AP Physics 1. And work is a scalar, so it can be any number. When the work is positive, there's energy transferred in the system, and when it's negative, the energy is transferred out to the system. The unit for work is joules, which can be denoted as capital J. This magnitude F is the magnitude of force acting on the object in Newton N. This magnitude of the delta X is the magnitude of the displacement vector in meter, and theta is the angle between the force vector and the displacement vector. When you're trying to find the net work is defined as the sum of the work, which is the net work, is equal to sum of the magnitude of the force times the magnitude of displacement times the cosine of the angle between the two vectors, which if you want you can write as the net force times the displacement times the cosine of the angle between the two vectors. Note that in equation sheet, it's usually FD cosine theta, but F and D must be positive. They cannot be negative. Along with a non-constant force, the area under the curve is the work done. For example, when you have a F and X curve, let's draw it better. Let's say you have like this. The force is not constant over this area, over this domain, or this region. So we have to find the area under this curve to calculate the work done over this distance. Next concept is on translational kinetic energy. Translational, which in this unit is always not rotation. Kinetic energy is measurement of energy possessed by an object when it's moving. When you're writing it, you can write capital K, or I usually write as capital KE, is equal to 1/2 and V squared. KE is the amount of kinetic energy in joules, M is the mass in kilogram, V is the object's speed, very important. Kinetic energy is always positive. 1/2 is positive, M is positive, V squared is positive. And it's a scalar. However, speed is dependent on the reference frame. When you change the reference frame, it also changes the kinetic energy. So to be aware of that. Work energy theorem. The change in kinetic energy is the net work done on a system. If you realize that the unit for work is joules, and the unit for kinetic energy is also joules. So they're equal to each other. The net work is equal to the changing kinetic energy, which can be written as 1/2 mv final squared times 1/2 mv initial squared, which you can simplify like this. It's very useful when calculating the velocity when there's a net force with a displacement. And next one is on conservative force. A force is conservative when the work done by a force is independent of its path. So what it means is that the work done is only dependent on the starting and ending configuration or the position. When the object is moving over a closed loop, then the net work is always 0 for a conservative force only. So when you're physics C, the work you can be written as an integral, and you have a circle in there, which means that it's over a closed loop. And the image for this, it shows how path 2, which is in purple, travels a much longer distance than path 1. But since the starting and the ending position are the same, the work done by this conservative force must be same. The example of conservative force, which are gravitational force and spring force. A non-conservative force is when the work done is dependent on the path, which means that the work done over a closed loop is non-zero. Choosing a different path might result in a different amount of work being done. So the example of conservative force includes friction and air friction and force applied by human. Non-conservative force is usually non-reversible, and conservative force is usually reversible. So it means, let's say you have 4 points, call it A, B, C, D. A, B, C, D. If you want to go to A to D, you got 2 paths to go. One is A, B, C, D. A, B, C, D. One's A, D. The amount of work done by the conservative force is always the same if you go to A, B, C, D or A, D. But for non-conservative, for example, friction, since it travels the longer distance, it will have a larger work done. And gravitational force is independent of path. Let's say you're having an incline. It has a length L. It has a angle theta from horizontal and a height h. You want to push this object up at constant velocity, and you're comparing the work for going up the same height h. Well, let's say sine theta is equal to h over L. So you know that h is equal to, actually let's leave like this. So the work done, work is equal to FD cosine theta. FD cosine theta. So what this is, if you analyze the force, it should be mg sine theta, mg sine theta times this length L, times this length L. But what is this? If we solve for h, it's equal to L sine theta. So this is actually equal to mgh. Let's see for this. For the second one, work, you still want constant velocity. Go to mg, which is the force, times the height h. You see, even though through an incline it has a higher, it travels a longer distance, but since it's a conservative force, it's the same work being done. Next one is on potential energy. An object can have potential energy, usually write as U or PE, to another object when the two objects are in the same system only. If it's in a different, if an object is on a different system, it cannot have potential energy. When stating the 0 point of potential energy, which you can change, you usually use one of the point for 0 for simplifying the problem. For calculation, you know that potential energy is a scalar which can be all real number. So first one is elastic potential energy. It's usually for spring. So say P sub S is equal to 1/2 K times delta X squared. This is the amount of potential energy. And next one is gravitational potential energy. We set the potential energy equals 0 when the distance of two objects is infinitely far. When the two objects in the system are approximately spherical distributed mass, then we can say the potential energy, let's write U sub G, equal to the minus G, that's the gravitational constant, M1, M2 over R. This negative means that the closer the objects are, there must be more kinetic and less potential. Since you want to balance the equation, as they get much closer, it will become more and more negative. And if you want the mechanical energy to be constant, there must be more kinetic. When the height is near a planet's surface, or you just know G, and so U sub G is equal to mg delta y. Delta y is the distance from equilibrium position. Or not equilibrium, sorry, it's from the 0 position. The total potential energy of a system containing two or more objects is the sum of the potential energy of each pair object within a system. So you got A, B, C. So you need to do minus G, M1, G, M, A, B over R. You have to do minus G, A, C over R, and you have to do minus G, C, B over R. That's what it means. You have to sum all these. And a system containing only one object can only have internal and kinetic energy. It doesn't have any potential energy since it must be in interaction with multiple objects. And next one is on the relationship between force and potential energy. So force is equal to the minus of the change in potential energy over change in time. Or this can be the slope of the potential energy versus time graph. And the relationship between work and potential energy is the work is the negative of the potential energy. Actually, let's write the change in potential energy. And let's talk about conservation of mechanical energy. So mechanical energy is the sum of kinetic energy and potential energy. So there's a kinetic energy KE, and there are two potential energies, gravitational potential energy and spring potential energy, or elastic potential energy. You can write it as 1/2 mv squared times mg delta y times 1/2 kx squared. For a system, any change of one form of energy must be balanced by changing other form of energy or by transferring energy between the system and the surroundings. The energy transfer from surroundings to object is done positive work. The energy transfer from objects surrounding to surrounding done negative work. For example, there are friction, heat, or sound. they're losing energies for these. For an isolated system, so let's talk about isolated system. A system is isolated, the mass, it cannot leave. It cannot leave the system. The energy can also not leave the system. So which means the mechanical energy is conserved. So for an isolated system or zero external work done, there's no conservative force interaction within a system. And so that the mechanical energy must be conserved, which means that change in mechanical energy is zero. So mechanical energy initial equal to mechanical energy final. And got this really, really long equation you usually have to use if you are working to solve for some other values. And if the work done on the system is not zero, which is done by non-conservative force usually, mechanical energy inertial plus the work by non-conservative force equal to the mechanical energy final. Which you got all these things. And finally, let's talk about power. A power, which is capital P, is a scalar. That's the rate of change of energy transfer with respect to time. Mean is that P is equal to the energy transfer is the work done with respect to time. So it's delta T, which is the changing energy over change in time. If you use the work equation, so that's F times delta X, the magnitude of them, times the cosine of the angle between the two vectors over delta T. For instantaneous power, we can take out this delta X and delta T. So the limit of delta T approaches 0 of delta X, the magnitude of it, over delta T. That's equal to the derivative of the magnitude of delta X over delta T, which is the speed, not velocity. When you substitute this back, see power is equal to the magnitude of force times velocity times the speed times cosine theta is equal to the magnitude of the force that's parallel to the speed times the speed, which is equal to the force times the speed, amount of speed that's parallel to the force. And that concludes my review for Unit 3, AP Physics 1 on energy, and I'll see you next time.